Okay, let's start the second day of the conference. And today we shall have Richard Hamilton, who got the prize for mathematics. Richard Hamilton has been my close friend for close to 50 years. And he is the founder of one of the most spectacular, important tool in geometry, the Ricci flow. And this is one of the most important tools that has started revolution for geometry bridge with topology in a much closer way than previous tools that we saw. So I think it's such a spectacular view that the jury has chosen him as our awardees. And I believe that this is certainly well deserved. The Ricci flow has solved many, many important problems, including the Poincare conjecture and the quarter pinching sphere theorem, which has been open for 60 years. There was absolutely no other ways to solve it except by using the Ricci flow. So many, many important questions have been solved by Ricci flow besides these two important conjectures. And Richard Hamilton is a key person into it. And Ricci flow does not die because it works in Kähler geometry and it works in four manifold. We were hoping that Ricci flow could be important for the four-dimensional Poincare conjecture, or at least the development of four-dimensional manifolds. This will take more efforts, and I assume that younger mathematicians in this audience probably will take up the torch. But anyway, it was a misled report by many reporters, either in news media or some magazines, that Hamilton started Ricci flow and did not do much until Perelman. It's absolute nonsense. I remember I met Richard Hamilton in 1978 in Cornell. Rick Shen and I was working on harmonic maps, and we were interested to know whether Ewes and Sampson's work can be reformulated in the space of metrics. Well, little do I know, when I met Hamilton, he actually has already started and even proving the local existence on the Ricci flow. So I thought that's great, but I thought I would wait until to see something serious coming up, namely global existence. And I thought that would be very difficult. And I don't believe that a man besides me and Rick can do it. To be frank, we were truly arrogant. And then by 1982, I got a phone call from Richard, who told me he could do the three-manifold case with positive Ricci curvature. That really shocked me and totally amazed by his argument. He'd come to Institute for Advanced Study and study the Ricci flow and give a big report. It was spectacular. I immediately get 3 of my graduate students to work on the subject, Kähler Ricci flow and curvature flow and all that, and start to look into what Hamilton done. And this is really spectacular, but then there's a long journey to go because we need to know how to pinching, how to not get rid of singularity, how to handle singularity and all that. So at that time, I knew there would be at least 20 years work in order to make it work. But I advised Hamilton, and he took it so serious, which amazed me also, that this would be eventually solve the Poincare conjecture and the geometrization. And he started to work on it and plan on it, and he started to do amazing work. There are a lot of obstacles he has to overcome. He overcome one by one. And some of this he will report today. By 1996, actually, when he proved that geometrization problem can be solved if the curvature is bounded, I see the rest should be doable, And so many people started work on it. We even applied money from NSF in America to form a center to treat this problem. Unfortunately, NSF did not approve the thing. Instead, they went to mathematical biology, which did not produce much. If NSF would fund the center in Hawaii, I'm sure we could have done much more than what we have done, well, in the last step, I mean. And so, of course, the great leader, Perelman, come in and provide really brilliant ideas and finish the last step. But even in the last step, there are quite a lot of people has made contribution to it to accomplish the final step. But anyway, the story has not stopped there because the Ricci flow is still continue to play a very important role. So Richard is going to tell you some more details. So Richard.
Thank you very much. Sheng-Teng Yao is a good friend of mine for many, many years now. And he was one of the first people, actually the first aside from myself, to recognize the importance of the Ricci flow. And he has done a great deal to promote me and my work on the subject and encourage many other talented students like my good friend Cao Haidong, who's done excellent work. So I think I'll start by telling you the story. How did I think of the Ricci flow? Well, there's always two ways the story goes: how someone should have thought of it and how they actually thought of it. So how I should have thought of it is that minus twice the Ricci curvature is actually a natural substitute for the Laplacian of the metric, which you can see by looking in harmonic coordinates. And so it's natural to write down the heat equation for a Riemannian metric as d dt of the metric is what would be the Laplacian of the metric, which turns out to be minus twice Ricci. That's not how I found it. I was motivated by the work of Ilse and Sampson on harmonic map flow. And when I got my first job at Cornell, Jim Ilse was there and lectured on it. And that's when I had to scramble around and learn some differential geometry, which I learned out of a lovely old book by Eisenhardt. And so anyway, I wanted to do something analogous. Oh, I don't need it yet. Let's see, where was I? I was motivated by Ilse and Sampson, and I thought it would be good to do a heat type equation for a Riemannian metric. So I thought, well, I'll start by writing down a Dirichlet energy, which would be length of the first derivative of the metric squared and doing the gradient flow. Unfortunately, as you all know, in the natural sense, the first derivative of the metric is the covariant derivative, which is 0. So that doesn't exactly work. However, there is a very useful principle in life, which I learned from my son, Andrew, who at the time had come up to visit me. He was a teenager in Ithaca, New York. I was teaching at Cornell, and I had a new car, and I had parked it overnight outside of a motel till I could move into my apartment. And some teenagers made an attempt to steal the wheels, and they had removed the lugs from the wheels, but they were scared off before they had time to actually get the wheels. So I got in the car with Andrew, and I started driving, and after about 2 feet, there was this loud clunk, and I got out and looked, and one of the wheels had fallen off the car. So I went back in the car, put my head in my hands, and my son Andrew said, "What's wrong, Daddy?" And I said, "The wheel just fell off the car." And he said, "That's okay, Dad. Let's just go anyway." So sometimes in life, when you get stuck, you try to see if you can go anyway. And in this case, I couldn't find the Dirichlet energy to do the gradient flow, but I thought, well, what would I do next? I thought, well, the gradient flow would involve a first derivative squared, and then when you would integrate by parts to do the gradient flow, you'd get something in second derivatives of the metric. And then the alarm bells went off. Ding, ding, ding. Hey, stupid. Two derivatives of the metric is a curvature. So I want to evolve the metric by a curvature. To show how brilliant I was, my first attempt was ddt of the metric is plus the Ricci curvature. And then I calculated ddt of the Riemannian curvature, and it started out as minus the Laplace of the Riemannian curvature. Clearly the wrong way. That, however, was easily solved by putting a minus sign in front of the Ricci curvature, which then led to ddt of the Riemannian curvature as plus the Laplace of the Riemannian curvature, plus lower order terms. And that got it well underway. So that's how I came up with the Ricci curvature. And it's turned out to be a very fortuitous discovery, because the Ricci curvature is really the natural form of the Laplacian of the metric. So it really is a heat equation for a metric. And what the regular heat equation for heat tries to spread the heat out equally over the domain, and the Ricci flow tries to spread the curvature out equally over the manifold. Now, I think at this point I can start doing my slides. Okay. So, I don't need to correct it. As you know, the Ricci curvature is a symmetric bilinear tensor on a manifold where for any orthonormal frame of VIs, the Ricci of V1 is the sum of the tangent planes spanned by V1 and Vk, where k goes from 2 to the dimension n. And the Ricci flow is evolving the metric by ddt of G is minus 2 Ricci, which, as I've told you, can be thought of as the heat equation for the metric. In the case where the dimension of the manifold is 3 and the initial Ricci curvature is positive, that actually happens. It's a great stroke of good luck if there happens to be a good theorem that you can grab quickly. Even if it's not everything, it kind of shows you can do something with it, and you're not a complete idiot. It reminds me of the greatest compliment I was ever paid, which was from my friend Xing-Tung Yao. And he confessed to me later, "Oh, when you first showed me the Ricci flow, I thought you were a madman." And I love the idea that I had an idea so original and out of the box that they would think I was mad. So thank you. And so so as I say, that the first theorem was there, easy to get, that in 3 dimensions, the Ricci flow will spread the curvature out, and the solution will exist for a finite time. But since the curvature is all positive, it shrinks down to a point in a finite time. You can have a rescale by the time to scaling, and then it will converge to constant positive curvature, which proves the theorem that if you have a 3-manifold with positive Ricci curvature, it's diffeomorphic to a sphere or a quotient of the sphere by a group of linear isometries. However, Yao pointed out to me that if you don't have that assumption, the Ricci flow can form singularities, and the simplest is a neck pinch. So if you imagine a dumbbell shape uh, object surface, and you have like the two spheres, well, let's make it S3 so that they're not too trivial, and you have a neck connecting them, then the neck looks like a cylinder, an S2 cross a unit interval, and where the cylinder is narrowest, the curvature will be the greatest in the two sphere, and that will cause that two sphere to shrink faster than the others, and that like closes down the neck and pops a hole. So some people suggested that you should deal with weak solutions and try to define weak solutions, and I guess you can do that. However, it happened, fortunate accident, that my father was a doctor and he was a real surgeon. Unlike me, I just have a PhD. What's the difference? Well, when I was a young kid, I would go to lunch downtown, and walking down the street, I could never go more than a block. But what two people came up to thank my dad and for saving their lives, and then they'd tell me how great my dad was. That was very nice. So anyway, being familiar with the idea of surgery, I thought rather than do weak solutions and deal with those difficulties, when it started pinching the neck, I would treat it the way my dad would treat something in the intestines. I would think of the part of the neck with the high curvature as becoming inflamed. And the thing to do is to go out a bit from the inflammation to where the curvature is less, and then go in and stop the Ricci flow. The manifold goes into the hospital, and I cut out the part there that curvature was big and sew it up with end caps and then start the flow again. And the idea is that you will only have to do this a finite number of times, and then the Ricci flow will go on and do what it wants, which would be to converge to some nice metrics. So that's how I came up with the surgery thing. So now, to make you more familiar with the Ricci flow, I thought it would be best just to give you some nice examples because it's a fairly abstract thing. And so we have ddt of the metric is minus twice Ricci. And the simplest example of the Ricci flow would be on an Einstein manifold, where the Ricci curvature is a multiple of the metric. And of course, if the multiple is zero, Ricci is zero, and then the Ricci flow doesn't do anything, which is kind of hard to describe, but it's because nothing is hard to describe. So anyway, the behavior of the Ricci flow depends on the sign of the constant. When the constant Ricci is constant, G is positive, the metric shrinks. So on a round sphere with equal sectional curvatures everywhere, it simply shrinks down, staying spherical until it collapses to a point. And there's the formulas for it. If C is, let's see, if C is negative, then you get the opposite thing. It will expand, and if you can trace it back to a Big Bang, and then it's like it all emerges from a single point and just grows and slows down growing and drifts off into nothingness, which is what I think the many physicists have said is supposed to happen to our universe. I myself find it rather disappointing to think that we're just destined to drift out into basically nothing. It was everything spread out evenly over a huge or infinite universe. Anyway, so those are the examples. So now to some more interesting examples. There's solutions of any flow that we call solitons. And I know that some physicists have said that it shouldn't really be called a soliton because they are very familiar with the theory of shallow waterways, where you get these things that move without changing their shape. And the thing there is that if you have two of them, one can catch up on the other, and then it forms a complicated waveform, and then they separate out again, and they come out like they look. Well, anyway, we call it a soliton if it moves without essentially changing its shape. And the classic example is the cigar, which has an explicit solution on the xy plane like this. And you'll notice in here that e to the 2t is describing the evolution in time. However, basically, if you add a constant to t, then this grows by a constant. And if you multiply x and y by constants, the quotient stays the same. So you can see that it's naturally isometric to what it was at any other time. And what it looks like is this thing. It kind of starts rounded off at the end, and then it goes on out to infinity. And I probably should have done a better picture here, because when I originally named this, I had it going out to a longer cylinder, and then I had written 3 wavy lines at the end of it to indicate that it went on forever. But then it looked like the smoke coming out of the end of a cigar, which is how I got the name. And there's 3 dimensions. There's a 3-dimensional solution that's a rotationally symmetric soliton opening like a paraboloid, and its existence was first proved by Robert Bryant. Then there's another more interesting one found by Eli at Berkeley. Well, we had conjectured this existed. He did the proof. And it looks like this, that only there's an extra dimension, because it's kind of hard to draw the 3 dimensions in 3 dimensions. So each curve here you should think of as rotating around to, and then these all look like a bunch of solitons lined up and going out to both ends at an angle. And I called it the flying wing because in the 1950s, the Air Force designed an experimental plane that the pictures were in the newspaper, and it looked like a single wing that would fly and take off. Okay, so now there's some nice examples of Ricci flow in 3 dimensions that are homogeneous spaces. And a simple example is the sphere S3 has a number of homogeneous metrics. So I'll remind you, a homogeneous metric is one where there's an isometry taking any point to any other point. So it looks the same at every point, but not the same in different directions. And you can compute this using these basic vector fields, A, B, and C in X, Y, U, V space. And they're arranged so that the Lie brackets come out nice. Lie bracket of A and B is 2C. Lie bracket of B and C is 2A. Lie bracket of C and A is 2B. And then if you look at the homogeneous metric with the diagonal elements like this, and if they have values alpha, beta, and gamma, then the Ricci flow turns into a system of ordinary differential equations, which you'll see here. There are various combinations of alpha, beta, and gamma. And then this I could solve numerically on my computer. By the way, I've named my computer. I've named her Muffin, and let me introduce her. Say hi, Muffin. Hi. Well, I spend a lot of time with her, and she seems rather like an intelligence, obviously not a human. How did I come up with the name Muffin? Well, my first computer was a big laptop, and it was a Macintosh, so I called him Big Mac. And then when I got a small laptop, I thought, well, what's smaller? And I thought Egg McMuffin, but I shortened it to Muffin. So here is a typical solution found numerically for the homogeneous metric on S4, where I start at 1, 2, and 7 for alpha, beta, and gamma. And you can see that they all decrease. That's because all the curvatures are positive, but they're approaching each other as you go to a collapse time. And there's another example that you can find, which is a homogeneous metric invariant under the Heisenberg group, which is this nilpotent group here. And here the metric is ds squared is t to the 1/3 times 3 dx squared plus dy squared plus t to the minus 1/3 dc minus x dy quantity squared. And it actually moves by a vector field, but the vector field is not a gradient. So this is a non-gradient soliton. Okay. And then there are solutions combining solitons, for which an explicit one was found by J.R. King, and it looks like this. ds squared is cosine squared psi d theta squared plus d psi squared over hyperbolic cotangent of the time capital T minus little t, and capital T is at n time, plus sine squared hyperbolic tangent of capital T minus little t. So it has a simple description. If you let time go back to minus infinity, then each end approaches a cigar, and the stuff in the middle approaches a cylinder, but in two-dimensional cylinder has no intrinsic curvature, so it can just sit there. And then as t goes to capital T, the two cigars move in towards each other till it joins up to look like a small sphere, and eventually it goes to a point at a finite time. So, so now I'll summarize formulas from the Ricci flow. So as you see, the metric evolves by minus twice Ricci. The volume element evolves by d dt of the volume element is minus the scalar curvature times the volume element. The length of a curve evolves by d dt of the length is minus the integral over the curve of the Ricci curvature. And here's the evolution of the Levi-Civita connection, and the elevation of the evolution of the Riemannian curvature, which looks rather complicated if you write it all out like that. But I found a nicer way to summarize it, in which you start by choosing an orthonormal frame for the tangent bundle, and then you evolve the frame to stay orthonormal using this formula. It's a simple exercise to check out that keeps it orthonormal. And then this is the evolution in the orthonormal frame, which looks a little simpler than in coordinates. And then there's a complicated way that you can do this. So you pick the frame like this, and then you write the curvature operator in the frame as a matrix M alpha beta, where the phi alpha and phi beta are a frame given a basis for the two forms. And then there's a nice formula for the evolution of the curvature operator, which is ddt of m alpha beta is Laplacian of m alpha beta plus m alpha beta squared plus m alpha beta sharp, where m alpha beta squared is just the normal matrix squared, and the m alpha beta sharp is a kind of square using the Lie algebra. And so we have Lie algebra constants like this, and these are the formulas. In dimension 2, it's easy enough. That's just ddt of r is Laplacian of r plus r squared. And in dimension 3, lambda 2, the 2 form says dimension 3. And if M has the diagonal matrix lambda mu and nu when you diagonalize it in a frame, then M squared is just the ordinary matrix squared, and M sharp is this unusual way of squaring the matrix, where you get mu nu, and lambda mu. And then there's more complicated formulas in dimension 4. And then we have commutator formulas for the heat operator and a covariant derivative like that. So that's an idea of how you compute. And I see I've only used up half of my time, but I've actually gone through all the material that I have here. So I think the first thing I could do is ask if people have any questions. And then I'll maybe make a few remarks on the future. Questions?
I saw a reference to your work concerning curve shortening algorithm, and actually curve shortening is related to a sort of flow, and it solves some problems like word and conjugacy problems in group theory. I wonder whether one can use not just length, but maybe heat equation, curvature flow, or some other things to solve problems in group theory or in algebra?
Oh, that's a great question. And I don't know the answer. I don't know much about group theory or algebra. I do know that there's a whole wide field of geometric flows now. And the curve shortening flow is basically a heat equation for a curve. And it flows every point on the curve with a velocity equal to the curvature in the normal direction. And it's an unusual, surprising theorem that if you start with an embedded curve, it will actually stay embedded up to the point that it straightens out to a little circle and shrinks to a point. And that was like greeted with skepticism at the beginning, because people drew examples of curves that would wind all around with a spiral and spiraling in and out, and thinking, well, how can it unwrap itself without doing a singularity? But it turns out it does. And so that's a beautiful example of a geometric flow. There's an interesting conjecture by a student of mine, Steve Altshuler, who worked on the curve shrinking flow in space. And for the curve shrinking flow in space, even with an embedded curve, you can form a singularity. And the way that happens is you can have a curve that comes down, makes a loop, and goes on, and the loop almost crosses itself, but it goes to one side or the other. And then if you play around with a one parameter family, you see that there has to be some curve there which is going to do something singular, and that one curve, instead of going straightening out to one side or the other, actually makes a cusp. So Steve Altshuler's conjecture is that generically, like for an open dense set of initial curves in space, you don't get any singularities. It would be a nice example of proving something that happens generically. I don't think we have many results in the field of geometric flows on generic behavior. Okay.
Are there other questions to ask Richard? Yeah.
Thank you for your wonderful talk. I just want to ask that if it's possible to take the time as another coordinate and consider a manifold with one dimension high and whether there are some good geometric structure on this possible high dimensional manifold. Thanks.
I guess I didn't quite understand.
So I just ask.
Well, maybe Yao can explain.
Sorry.
Relativity, where space and time put together.
Oh,
like general relativity.
Thanks.
Well, the thing with general relativity is that it has a Heisenberg metric. One of the dimensions that time usually is counts as ds squared is dx squared plus dy squared plus dz squared minus dt squared. And that leads to hyperbolic type equations. They're not exactly hyperbolic, but they're similar, and they can produce singularities. But if you tried to run Ricci flow on a Heisenberg metric, you'd encounter a problem that in the time-like directions, you would be running a backwards parabolic flow. And you can't solve a parabolic equation backwards. If you try to solve df dt as minus Laplace f, well, what happens is with ddt equals plus Laplace f, the high frequencies decay away fastest. But with the negative equation, df dt is minus Laplace f, then the highest frequencies blow up fastest and you just get garbage. So I don't know how to reasonably answer that.
Okay, other questions?
Okay, thanks. Also, thanks, Professor
No,
Yeo.
sit down, please. Other questions? Yeah. Richard.
I think the last question was not intended to be about Ricci flow in Lorentz signature. Rather, the questioner was asking the following. If you have an n-dimensional Riemannian manifold, and you take a one-parameter family of metrics due to the Ricci flow, do you get something that you can usefully regard as a geometrical structure in n+1 dimensions?
Oh.
I think that was the intended question.
Yeah. You could certainly regard it as that, but I don't know that it would. I mean, you're not actually getting a normal Riemannian metric in space-time. So I guess I don't know how you would profit from it.
It's too much useful to look at it that way. Okay, other questions? Well, if not, Richard, you want to continue, or you want to make remarks?
I've run out of the material that I prepared because of some problems with the computer, but I'll make some other remarks. One thing is that there has been recent progress on the curvature pinching. And the original work by Klingenberg was on quarter pinching, making it homogeneous to a sphere if it's simply connected. So there's a lovely work by Rick Shane and Simone Brendla on doing versions that are conditions that are stronger than quarter pinching, imply quarter pinching, but under Ricci flow evolve to nice round things. And that's worth mentioning. Yeah. And also there's, various other estimates that are useful for Ricci flow that are rather technical. But one is the Harnack estimate. And the Harnack estimate is you have to prove it as a matrix inequality. But the ordinary Harnack estimate for the heat equation basically is that df dt plus 2f 2 df dot v plus f length v squared is going to be plus 1 over tf is greater than equal to 0. And that has nice implications. And we have a Harnack estimate for the Ricci flow. And we also have a logarithmic Sobolev inequality, which is due to Perelman. Perelman is a very clever fellow. And he has a slight version on the logarithmic Sobolev quantity in which he includes the scalar curvature. And then its evolution under the Ricci flow is you just do ddt of this logarithmic Sobolev quantity. I won't want to call it a constant because we always talk about the Sobolev constant, but you can't talk about the constant evolving so easily. So anyway, it's a very nice result, which implies that if you have a pinching condition initially, volume pinching, so you assume the volume of a ball of radius r for small r is at least some constant kappa times r to the n, that you then get, if that estimate is true for an initial time, you can say that you get a similar estimate for a later time, but the constant kappa has to change, and it's going to decrease exponentially. So that means that when you do limits of Ricci flow, they can be collapsing. And one way to deal with that is you have to expand not just to control the curvature, but also to control the volumes. So there's a bunch of stuff that can be done that way. We have these nice, powerful estimates. Okay. I also had a version of a universal pinching estimate. That the pinching is that if you run Ricci flow, say in some dimension, like in 3, it can have some negative curvature, but the negative curvatures tend to come up, and they kind of get all pushed towards non-negative. So, yeah, that's an interesting idea. Lots of other interesting ideas, lots of problems to work on. In 4 dimensions, I and others have worked on hypothesis of positive isotropic curvature in 4 dimensions, and that produces useful results. Any other questions?
Yeah, so perhaps we could ask more questions. Some questions for fun. Yeah.
Can we apply the Ricci flow to prove the Stokes conjecture on positive Ricci curvature?
To the What conjecture?
Stott's conjecture on positive Ricci curvature.
Stars?
Nobody, can you explain exactly what you said? I don't quite catch what you said. What conjecture?
Stott's
What?
conjecture on positive Ricci curvature and the stream Boson.
You mean the sole conjecture that was done by Perelman many years ago?
No. The positive Ricci curvature and the stream Boson. The relation between stream Boson and the positive Ricci curvature.
I don't quite understand exactly what you state the conjecture, the statement.
No, Stott's.
Can you state exactly what the conjecture is? You mentioned the Stotts, okay? Make a statement.
The manifold admits positive Ricci curvature if and only if the Witten genus vanishes.
What dimension? All dimension or dimension 4?
No, any dimension larger than or equal to 5.
So you say that she conjectured that manifold has positive Ricci curvature, even only if the Witten genus is equal to 0. I thought that makes an assumption on the Pontryagin class. Assume the first Pontryagin class equals 0.
Yes, yes. It requires the string structure.
Yeah.
1/2 P1 equals 0.
Yeah. Well, Richard, so there was a conjecture which I don't believe is true, is that if I assume the manifold have first Pontryagin class equals 0, then
First what class?
First, number 1, Pontryagin class.
Quadratic.
The,
Pontryagin class.
Yeah.
Okay.
Then the manifold admits positive Ricci curvature if and only if some topological invariant Witten genus equals 0.
Well, if you were trying to prove that with Ricci flow, you kind of need a metric to start with.
Right.
And it's not clear where you would start. And if you just start at random, you're likely to get neck pinch singularities.
So maybe I add to the comment because the work, the Wise 3-dimensional work is because Ricci positivity is preserved. Once you go on dimension 4 or more, it's no longer the case that Ricci will be preserved. So even you assume at time t equals to 0, you get positive Ricci curvature, it will probably does not, for once you evolve. So it's not clear, right, Richard?
Yeah.
Thank you.
Probably have to be by other means.
Okay. Other questions? Any questions for fun? Yeah.
Richard, can you comment on other curvature flow that might have applications in other areas?
Well, I can tell you the various curvature flows I've thought of. Certainly the most important is the mean curvature flow. And the difference is with Ricci flow, you just have an abstract manifold. It doesn't have to be in a Euclidean space. And if it did, the Euclidean space would have nothing to do with it. The mean curvature flow, well, Ricci curvature is an intrinsic curvature. Mean curvature is an extrinsic curvature, meaning it describes how the manifold curves in an enveloping Euclidean space. And I like to think of the Ricci flow and the mean curvature flow as twins, but not identical twins. In that I think they kind of seem to share half of the DNA. That half of the things that work for Ricci flow also work in mean curvature flow, and half are just totally different. I know my good friend Gerhard Huisken has done a lot of good stuff on mean curvature flow, as well as many others. I was lucky that back when shortly after I'd first moved to San Diego, and while Yao and Rick were still there, Gerhard Huisken came to visit in San Diego, and I got to work with him for a whole year, and we discussed a number of ideas like limits of manifolds, for which I have to thank Rick Shane for a very good tutorial, and compared the different things between the mean curvature flow and the Ricci flow. So, and as far as applications, I don't really know. There was one application which used the inverse mean curvature flow, where you flow the manifold by -1 over the mean curvature. That was used to prove, I think, the Penrose conjecture. And that was nice. It involves singularities. Yeah.
Well, actually, the mean curvature flow is related to Ricci flow for bundles in a more precise manner. Under Miller symmetry, the mean curvature flow, the special Lagrangian cycle, is actually Miller to the Ricci flow for bundles, for Hermitian-Young metric. So that was more or less can be proven in some way to be the case, although it's still a conjecture. It's a conjecture that Richard Thomas and I made 30 years ago. So far is fine. The only thing I can say. Any questions? Yeah.
Hi, thank you for the wonderful talk. Real quick, because I can't help myself, is your cell phone called McNugget?
Well, I hadn't thought of that, but maybe it's a good idea. After the talk, I'll ask my cell phone. He wants to be McNugget.
So my real question is, if you wanted to consider the Ricci flow on, say, a manifold with boundary, or maybe just on a certain subset of, a larger manifold, are there any boundary conditions that you would need to consider or impose in order for that to be kind of a well-formed idea?
I thought for a while about boundary conditions. Curiously enough, in my youth, I often made a career out of taking other results that people had done without a boundary and doing the similar result with a boundary. For example, my book on harmonic maps of manifolds with boundary. What I've tried with the Ricci flow, I think it makes sense to have the Dirichlet condition of trying to specify the metric on the boundary. I'm trying to remember. I think there's something like it's a different number. I think you have to specify one less boundary condition. God, that was a long time ago. But I never really found one that seemed particularly useful. I think that Dirichlet boundary conditions make sense, but the Neumann boundary condition only made sense if you could double the manifold to account for that. Yeah.
Thank you.
Okay. Other questions? Yeah.
I'm asking a question about applying Ricci flow to four manifold. So if you have a Ricci flow or some kind of generalized Ricci flow, for four manifold, you have long time existence. It may lead to a complex manifold or symplectic manifold. and with divisors or cycles cut out. Can you make some comment on this four manifold?
Well, I've worked on a bit on Ricci flow on four manifolds with positive isotropic curvature, which is an unusual curvature condition, but it seems to, it's preserved under Ricci flow. It will lead to good convergent results. And aside from that, I don't know. But it's certainly an interesting thing to study. And
yeah.
Okay,
Yeah.
Next. Yeah. The back. Hold on now. Some people in the back.
Hi, can you say something about the four-dimensional Poincare conjecture, whether Ricci flow will, the advantage of Ricci flow to solve it or the obstructions?
4D Poincare conjecture, was it?
Yes.
Gee, that would be nice. I think that it would be hard. I think that there's a lot of structure that can go on in four manifolds, and one would have to figure out how to deal with singularities. But I think it's potentially very useful because in four dimensions, let's see, you get two possible singularities. You get the classic next pinch, where an S3 cross R1 pinches down, and let's see, and then there's a hole punch singularity, which you can envision in the following way. You take a sheet of two spheres over the two plane and imagine that the smallest sphere is at the origin and the spheres grow in size as you go out away from the origin. Then the small sphere will shrink fastest and it will close down to a point, and then the ones around it will close down, and you'll get this disk where the spheres have all collapsed and it's opening up a hole in the manifold. So that's certainly a very interesting singularity, and it's going to be a lot harder to study than the neck pinch. Like, for one thing, if you try to do surgery on it, where would you cut that you could get very irregular shapes to where the hole has formed? I've discussed that with Huisken, but I don't know that anybody's been able to do anything with it yet. If somebody in here has, please come see me.
Carl want to say a comment.
Maybe I add a couple of comments. First of all, as Richard said, the singularity will be besides S3 cross the interval, that's neck pinch, you will have S2 cross two-dimensional, like R2 or square. So that's what he called a hole punch, and that is very tough singularity, how to do surgery. Second, I want to say is even in 3 dimension, the simply connectedness assumption was not used in the, say, Poincare conjecture in the process. So how that simply connectedness was used is at the very end. So you do the Ricci flow and analyze singularity and do the surgery, and then if it's the compact case, you have the finite. You got the finite extinction time proved by Paraman and also different proved by Cody-Minikowski. And then you know basically how the free manifold look like. It's the connect sum of special pieces. And then you look at those lists and apply the simply connectedness. Aha, that must be S3. And that's how is simply connected was used. So maybe one should, even for 3-dimensional or in the case 4-dimension, is explore whether one could more effectively use the simply connectedness assumption. And that is will be a great, yeah.
Real quick, one more remark, that if you did Ricci flow on a 5-dimensional manifold, then there's a surgery that you can do, which is, I guess, B3 cross S2 going into B2 cross S3. So the surgery can do itself both forward and backwards. And in that case, you probably are not going to be able to control the topology up to diffeomorphism.
I think the Poincare conjecture 4-dimensional manifold is probably better changed to replacing the S4 by CP2, complex projective 2-dimensional space, because that one involves complex geometry, and complex geometry, we know CP2 is rigid. Once you know it's diffeomorphic CP2, then it's actually the standard metric, more or less. And once you use the anti-Scherf-Due part of the curvature much more extensively, which so far has not been used. And there is a paper by Cliff Taus, written about 30 years ago. He proved that after stabilized 4-manifold, there exists a anti-Scherf-Due metric. This paper has not been recognized by most people, which should be recognized, I think, because anti-Scherf-Due condension is very important, and so far has not been used.
May I add? Yeah. So actually, Professor Hamilton has proposed a problem precisely using Tauf's work that Professor Yao mentioned. So this will be something called half PIC. Maybe I'll explain in my lecture tomorrow.
Sure.
Yeah.
Okay. Other questions? Yeah.
Thank you very much for your wonderful talk. So can you comment on the existence of non-Einstein compact Ricci soliton? Thank you.
Non-compact Einstein Ricci soliton.
A non-Einstein compact Ricci soliton, because it seems rarer than the compact Einstein.
Ricci soliton that are not Einstein metric.
That starts in dimension 4. And actually, on dimension 4, we have 2 examples, but they are both scalar. So one is on CP2 block 1 point, which Koizo and I found in late 80s and early 90s. And the second one is CP2 block 2 points. And that was by Xu Jiawan and Xiaohua Zhu about 20 years ago. So those are actually, so far, the compact example, we only have those 2, and there'll be 2 non-compact. And they are all scalar. So far, we only know scalar examples. So there's a classification in dimension 4. The shrinking examples are precisely 2 compact and 2 non-compact ones. And it's an interesting question whether there will be any non-scalar ones in dimension 4, and that remains to be seen.
Okay, next question. Yeah.
One application of Ricci flow in physics is that it's the renormalization group flow of the 2D nonlinear sigma model, and but it's only the one loop renormalization group flow, and this so there are some higher loop corrections. I wonder maybe this can suggest some variant of Ricci flow, and whether this will be useful also in mathematics.
Oh, yeah. I was trying to learn a little bit about that. There was, I think, a paper of Dan Friedan who pointed out that Ricci flow was what the one loop approximation to the renormalization group. And maybe a two-loop approximation would be interested, but I think that led to a fourth-order PDE. And it's much harder to analyze fourth-order PDEs. It would be a very good field of study, but the problem is you don't get the maximum principle. So our main tool is missing.
Okay, I think time is up, and we thank Richard for a beautiful talk. We come back at 9:45. Thank you.